conservation of momentum. All right, so, all right, so first of all, just a couple quick terms, including this definition of conservation of momentum. All right, so conservation of momentum says in the absence of external forces, the total momentum of a system will always remain constant. All right, very, very textbooky definition there. Right? So in order for that to make sense, a couple quick definitions, and I think we've learned these when we were doing courses. So these are hopefully review for you. But so first of all, a system. So when you look at a problem, you need to decide what objects am I going to consider as I'm solving this problem. Okay? And that collection of objects is going to define your system. All right? And then an external force, as the name would imply, is any force that comes from outside the system. Cool? All right. So we're going to be looking at two different types of interactions between objects. We're going to look at collisions, where the two objects crash into each other, and they may, like in that case, they stuck together. That's what's called a completely inelastic collision. We'll talk about that in a minute. Sometimes they'll bounce off of each other. Okay? So there's collisions we'll talk about, and then we'll also talk about what are called explosions, which basically just means that one of the objects pushes off of the other. So like this. Cool? Alright, so explosion. Alright? So in both cases, whether you're talking about a collision or an explosion, the two objects are interacting with each other. Okay? So here's your two objects, right? So here's object A and object B, right? Now remember, yesterday we had that problem where we had the two objects bumping into each other. All right, the first question was, which object exerts more force on the other? They're equal, right? So they're both going to have the same amount of force due to the collision. All right? Which one's in contact with the other for more time? They're the same, right? So you're going to, So you're going to have the same change in momentum, right? With one tiny little exception that we neglected yesterday. Point for me, which direction is object A going to push object B? Which direction is object B going to push object A? Which means that this force is negative. Okay? So the idea is one of our objects is going to have a negative impulse, and the other one's going to have a positive impulse, but numerically they're the same. Right? So the object that has a negative impulse is losing momentum, and the one that has a positive impulse is gaining momentum. Right? But the change is equal. So in other words, due to the two objects exerting forces on each other, one object might lose 10 units of momentum, the other one's going to gain 10 units of momentum, but the total momentum stays constant, right? All you've done is you've transferred momentum from one object to the other. All right. So we'll do some numeric examples, and I'll do some demos and stuff here. Before I do, so usually when I teach this class for regular physics, I take, half of the day, half of the class period, and I do this really silly little activity that is designed to help students understand what we mean when we talk about conservation of quantity. Okay? It's something that comes up a lot in science, right? Later on, we're going to talk about conservation of energy. This section is about conservation of momentum. Right? And usually when you talk about conservation of some quantity, you're just saying that the total amount doesn't change. Okay? So the activity that I do is I this works. The reason conservation of momentum works is because of Newton's third law. It's because these two forces are equal and opposite. Good? All right, that is important. Make sure you understand that this is a direct consequence of the third law. Okay, so probably the easiest way to do this is to just jump in and do an example. All right? So this first example, we're actually going to do it twice. I'm going to do it once in a lot of detail, all right, to sort of show you conceptually what's going on. All right? Then I'm going to go back and do it again. I don't think those work, Teddy. Use the plug back here. Yeah, I don't think those work. Sorry, what was I saying? So we're going to do it once in a lot of detail with a lot of like little calculations so you can kind of see what's going on. And then I'll go back and I'll show you the way that I want you to do it on the homework. Okay? So the first time that I'm doing this is just to help you see sort of what's going on. Cool. And then you'll learn the sort of streamlined way of solving. Good? Okay, cool. So, like I said at the beginning, if you make a mistake, 99% of the mistakes in this section are just missing negatives. So the first thing I want you to do is make it wrong. Okay, so here we go. We got a 1,200 kilogram truck. It's rolling at 5 meters a second when it collides head-on with a 500 kilogram car rolling at 8 meters a second. So head-on implies that they're going toward each other, right? Okay, so let's draw it. So here we go. Truck, 1,200 kilograms. I'm going to call it T for truck. Over here we've got a car, 500 kilograms, small car. C for car. Okay, so what makes this a little bit confusing is there are a lot of variables to keep track of because there's going to be 4 different velocities, right? The truck is going to have some initial velocity before it hits the car, and the car is going to have an initial velocity before it hits the truck. Then, after the collision, they're both going to have a final velocity. Okay, so there's a lot of numbers to keep track of. All right, so let's see. The 5 meters a second, that represents the velocity of the truck initially. Okay, and it's going to collide with a 500 kilogram car rolling at 8 meters a second. It's head on, so the velocity of the car initially, before the collision, is 8 meters a second. And then it says immediately after the collision, the car is going backward at 3 meters a second. So the velocity of the car final is 3 meters a second. Right. Now, because the car is going backward, that means, don't write it down, listen. Because the car is going backward, does that mean that its final velocity is negative? No. All right. When you solve these problems, you need to start at the beginning and you need to decide, all right, one of those directions is positive, one of them is negative. And then stick with it for the whole problem. So, which way do we usually make positive? This way, right? Positive, negative. So, from this point forward, anytime I've got an arrow going that way, I'm going to make it negative. So, which of these numbers should be negative? The 8 should be negative. Be careful, that can be misleading, right? Because you're thinking, wait a minute, the car's going backward. But because backward for the car is that way, it's still a positive direction. Make sense? In other words, it doesn't really matter which way the car is facing, right? What we care about is the direction the car is moving. Any problems? Yeah. You could make these negative and this positive, and that would be acceptable also. Is that what you're asking? Yeah. Yeah, and that would just be like if you flip-flop the whole wrong. Yeah, so again, you might, as you're solving the problems, you might get a positive answer and I get a negative answer, or vice versa. That's okay. Okay. Unless the problem explicitly says, like, these two plus or something. Good. All right. And then the question says, find the final velocity of the truck. So we're looking for the velocity of the truck final. All right. Are there any questions? Okay, so the law of conservation of momentum tells us that, and I wish I'd written this on the previous slide. Would you guys hate me if I jumped back a page? I'm going to do it. Watch me go. There, I did it. All right. Law of conservation of momentum. It says, in the absence of external forces, expression is this. Total, right? That usually we do EF, like net force. Net means total force, right? Okay. So this means total momentum initially. In other words, the total amount of momentum in my system before the two objects interact has got to equal the total momentum in the system after the two objects interact, as long as there are no external forces. Great. So what I'm going to do then is, let's go back to this drawing, and what I'm going to do is, for each of these velocities, there's a corresponding velocity. For each of these velocities, there's a corresponding momentum, right? So momentum is mass times velocity. So before the collision, for example, the truck has this velocity. That means it has some amount of momentum. Similarly, before the collision, the car has this velocity, and so it has some amount of momentum. Follow? So I'm going to go through and I'm going to find each of these momentums. All right? So I'm going to do something that you can't do, and I apologize. All right. So what I'm going to do is I'm going to find the momentum of the truck initially. And then I'm going to find the momentum of the car initially. I'll give you a second to figure out how you want to do that in your notes. I should have warned you. All right. So what two numbers am I going to multiply to find the momentum of the truck before the collision? Which mass, which velocity? Mass is 1200, the velocity is 5, right? So I'm going to skip units just to save time and space. So that gives us what? 6,000, right? Kilogram meters a second. Questions about what I did there? All right, let's do the same thing for the car. To find the momentum of the car initially, I'm going to do mass times velocity. So that's going to be 500 kilograms times negative 8 gives me negative 4,000, right? Good. I did not do a great job anticipating board space here. Okay. All right, so is everybody good with what I've done so far? All right. So look, what we just figured out is before the collision, the truck had 6,000 units of momentum. Hello, is Mr. Ecker? After class? Okay. Will do. Ms. Moreland? Okay. Sounds good. Thanks. Bye. After class. Okay, so here's what we just figured out, you guys. Before the collision, the truck has 6,000 units of momentum. I'm saying units just because kilogram meters a second in the next keep saying. All right, so before the collision, the truck has 6,000 units of momentum. The car has negative 4,000 units of momentum. Okay, when we got to the island, I had $6,000 in my wallet, and Jake had negative $4,000 in his wallet. Sorry. All right? What's the total? Well, add them up. So here's my total. Oops. Here's my total momentum before the collision. It's 6,000 plus negative 4,000, so 2,000. Does that make sense? Correct. Now, when they collide, some of the momentum of the truck is going to get transferred to the car, or vice versa, but the total has to stay the same. All right, so now what I'm going to do is I'm going to look at what's happening after the collision. So let's see, the momentum of the truck final, I can't find it because I don't know the velocity. So let's leave that blank for a second. Okay. Am I going too quick? Are we okay? We good? All right. Now we can find the momentum of the kilogram meters a second. Okay, so Jake has $1,500 now. Okay, we started out with 2,000. So if Jake's got 1,500, how much do I have? 500, right? The total has to stay the same. So the idea is this total momentum comes down. This total momentum, it started at 2,000. It's got to stay 2,000. Follow? Okay. All right, so that means that the momentum of the truck after the collision has got to be 2,000 minus 1,500, which gives me 500 kilogram meters a second. So I'm one teeny tiny step away from being done. What's the last thing I'm going to do? Now I can find that velocity, right? So P equals mv. Let's see, my momentum is 500. The mass is 1,200. The velocity is what I'm looking for. So divide. The velocity of the truck final turns out to be 500 over 1,200 gives like 0.417, is that right? And it's actually, I think, 0.416 repeating, yeah? But whatever. Cool? Sorry? A lot of numbers, but none of it's, yeah, none of it's rocket science. Just keeping your numbers straight, right? Watching the positives and negatives. All right, are there questions? Happy, okay? Yeah. Good, that was going to be my next question. Notice, if you keep track of your signs, your answer not only tells you how fast the car is going, but it tells you the direction for truck. And since we got a positive answer, that means it's still going forward. How is that possible? Why would the truck still be going forward? Yeah, it's got more mass, right? So it's this. Let's see, we've got a truck and a car, right? And I'm going to try to make the car go a little bit faster. Slow, a little bit faster. There we go. Cool. Okay, so there are a lot of variables, so there's no way I can exactly model it, but that's the idea. All right, I want to point out one other thing. So remember, again, why does conservation of momentum happen? What's it founded on? Newton's third law, right? Right? Remember, we learned that the change in momentum should be equal and opposite. So let's do this. Let's take a second and find the change in momentum for the truck and find the change in momentum for the car. So note. All right, so the change in momentum for the truck would be, what two numbers would I subtract? I'm going to find the change in momentum for the truck. Yeah, I should do the final momentum of the truck minus the initial momentum of the truck. So 500 minus 6,000, right? So that gives me negative 5,500 kilogram meters a second. Notice that's change in momentum, not change in velocity. That's the other common mistake. Sometimes people use velocity instead of momentum. Don't do that. Anytime you find change, it's always final minus initial. Good? Everybody good with that? All right, now let's find the change in momentum for the car. That should be the final momentum of the car minus the starting momentum of the car. So what's the final momentum of the car, you guys? 1,500. Minus, what was the initial? Negative 4,000. Minus a negative becomes plus. We're going to get positive 5,500. Why am I happy? They're equal and opposite, right? The car gained 5,500 units of momentum, and the truck lost 5,500. jump back a minute ago, I said here's law of conservation of momentum written in shorthand. This is one way of writing it, saying that the total of your objects before the collision is equal to the total of your objects after the collision. Another way of doing it is to say this: the change in momentum for object A is equal but opposite to the change in momentum for object B. Okay? Whatever's gained by one is lost by the other. I'll tell you that problem solving wise, this one is way better. Because this only works if there's two objects. This will work if you've got any number of objects. You can always just add up all the momentums before the objects interact, add them all after. Cool. Are there questions about what's up on the board? Okay. Alrighty then, let's do it again. Hooray! Oh no. Alright, so we're going to do the exact same thing again, but that chart gets a little bit cumbersome. Okay? So, here's the idea. I'm going to kind of recreate that same drawing that we had. So here's the car. No, we had the truck over here before, didn't we? So here's the truck. It's 1,200 kilograms. The velocity of the truck initially is 5 meters a second. The velocity of the truck final is what we're looking for. Here's the car, 500 kilograms. The velocity of the car initially is negative 3 meters a second. No, negative 8, sorry. That's an 8. Deal with it. The velocity of the car final is positive 3 meters a second. I'll fix my 8. And this time I'm not going to do any shenanigans moving my drawing around. Okay, so we good? Oh, some people are still writing. I'll give them a minute. I will enjoy some lovely water. Yes, I know. You guys try it. Great. All right, everybody good? All right, so what I'm going to do here is I'm going to take that giant chart that we just had and I'm going to put it into one big equation. All right? Which is going to seem intimidating, but once you've used it a few times, it's going to just be like kind of second nature. Yeah. All right? So check it out. Here's what I know. I know that, is everybody done writing this before I go on? All right, so I know that the total momentum of the two objects before the collision has got to equal the total momentum of the two objects after the collision, right? All right, well, what do I mean when I say total momentum initially? Well, that means the momentum of the truck initially plus the momentum of the car initially, right? And that's got to equal the total momentum after. Oh, well, that means the momentum of the truck after the collision plus the momentum of the car after the collision. A lot of letters, so pause, take a breath, and make sure you understand what all the letters mean. T is momentum, T is truck, C is car, I and F are initial and final. Any questions about that equation type? All right, so here's where it gets ugly. I'm going to replace P with, what's the equation for momentum? P equals mass initials equals all of your finals, right? Any problems? All right, let's plug in our numbers. Here we go. Let's see, mass of the truck. So we're going to get 1,200 times 5 plus 500 times negative 8 equals 1,200 times VTF. Oh no, I'm going to run out of room. Plus 500 times 3. Just barely squeezed it in there. Close. Everybody good? Negatives are super important. If you miss that one negative, you're totally screwed. Let me see max. All right. Oh, see max. That's what kind of car I got. Ford. It's electric. It doesn't work very well. All right. Everybody good? All right. So here we go. So simplify it. 1,200 times 5. Oh, that's 6,000. What is that 6,000, you guys? That's the starting momentum of the truck, right? Let's see. 500 times negative 8, that's minus 4,000. That's the starting momentum of the car, right? Equals 1,200 times the velocity of the truck final plus 1,500, right? So each of the numbers here, this is initial momentum of the truck, initial momentum of the car, final momentum of the truck, final momentum of the car. 2,000. What's the 2,000? The net momentum initially, total momentum initially is what we call it, but it's the same idea. Equals 1,200 VTF plus 1,500. So now algebra. Subtract 1,500. And you get 500 equals 1,200 VTF, and then divide. You get obviously the same answer. You have to put smiley face. Good, you guys? Questions? Any problems? All right, one last problem to do. It's easy. But then there's a point. There's a reason I'm doing it. No, it's not. It's not. All right, so this time, instead of the two objects bouncing off of each other, they're going to stick together. All right, so we're going to solve it using that same equation we used a minute ago. But, very good, they're going to have the same final velocity. So a lot of times people get confused because when you solve the equation, it looks like there's two unknowns, but there aren't. So, so they're going to stick together like this. Okay? So, your drawing is the same. So you've got your truck, 1,200 kilograms. The velocity of the truck initially is 5 meters a second. Here's your car, 500 kilograms. The velocity of the car initially is negative 8 meters a second. During the collision, the two vehicles stick together. Find the velocity at which they are moving after the collision. So the idea is, we don't know the final velocity of the truck, and we don't know the final velocity of the car. But like Josh said, we know they're equal. So don't distinguish between the car and the truck. Just call it VF. Right? You're finding the final velocity of the system. Make sense? Yep. For not writing all of this out. I mean, ultimately, as long as you get the right answer, I don't care. I will say you are less likely to make mistakes if you are more thorough. But, all right, everybody good? same big equation. So the mass of the truck times the velocity of the truck initially plus the mass of the car times the velocity of the car initially equals the mass of the truck times the velocity of the truck final plus the mass of the car times the velocity of the car final. It's the exact same big equation I used a minute ago. Yeah, sorry. All right, everybody good? Parker? Yeah, that's basically what's going to happen in one of the steps here. You'll see where that happens, but yes. All right, so let's plug in our numbers. Mass of the truck, 1,200. Velocity of the truck, 5. Mass of the car, 500. Velocity of the car, -8. Equals mass of the truck, 1,200. Velocity of the truck final, what should I put? Just VF, right? Final velocity of everything. Plus the mass of the car, 500, times what should that velocity be? Also VF. All right, so over here we get 6,000 minus 4,000 equals, super quick algebra lesson, what's 4x plus 3x? 7x. What's 1200V plus 500V? 1700V. Sorry. VF in after. So that's it, right? So that's what you were talking about. This is our combined mass, right? That's the mass of the system. So you get 2,000 equals 1,700 VF. Divide both sides, and your VF turns out to be 1 point something. 1.18, I got. Meters a second. There you go. Sorry? Questions on it? So once you get familiar with using this equation, the problems don't take that long. All right? So 6.2a is due tomorrow. I don't think it's quite as bad as it looks. Here's one thing that we did not do today that comes up on the homework in a few of the problems. There are some hidden zeros. Okay? Check it out real fast. I'm not going to do an example because I think you guys would get it. But look. What's my total momentum right now? 0. Oh, stop rolling. My track apparently is not flat. All right, pretend that it's not moving. So right now the total momentum is 0, right? Total momentum is still 0. Positive momentum, negative momentum. Follow? Good? You didn't understand that. Okay. Yes. Let me explain that real quick. Oh, real quick, here's a couple definitions. We can talk about this more later. It doesn't affect the homework. Sorry? Oh, gotcha. Are you good or no? No. Okay. So let's suppose that this is whatever 1.5 kilograms, and that this is 0.5 kilograms, right? We'll call this cart A and call this cart B. So before I pushed the plunger, the velocity of A initially was 0, and the velocity of B initially was 0, right? That means the momentum of A initially is 0, and the momentum of B initially is 0. So my total initial momentum is 0. So that's this. Right? So right now everybody's got a momentum of 0, right? Then when I push the plunger, this one springs that way, that one springs that way. So suppose, hypothetically, that this obviously is not realistic, but suppose that cart B springs that way 12 meters a second. Well, that means that this one is going to spring this way at some velocity, right? final. Oh, well, that's mass times velocity. So 0.5 times 12 is 6. Right? So what does the momentum of A afterwards have to be? Close. Enough that I'll write it. Negative, because they have to add up to 0. So now that I know that momentum, I can find the velocity. Follow? Right? So there are going to be problems like that where they're hidden zeros. Huh? Oh. When I went to school, that's one of the things they teach us, how they perfectly work out negative numbers. Good. The whole semester I got an A. All right. So now we just do P equals mv and solve for the velocity, right? So negative 6 equals 1.5 times v, and your v ends up being